son Marshall and Radar, little zapper gun. Phase should be thought of as a time delay. If something is out of phase, it means it's lagging in time. If something, you saw that with the three-phase power generator. You got three sets of windings evenly separated from each other around the center of a generating station's power source. And what you have, of course, is a 120 electrical degree delay from each one to the next. And that's the phase relationship. It says you're going to go through 360-degree cycles, but one's going to start 120 degrees later, and the next one's going to start 240 degrees later, and then the third one will be 360 degrees later, which is back to zero again. And picture's worth 1,000 words. That diagram, start throwing these away. Maybe it's because something about the board. Anyway, that diagram looked like this. Then there was a delay of the next wave and the next one, and so on. Where you have a 360-degree completion here, and here, and here, but each one is 1/3 of a cycle later than the other. That's what phase is all about. When you happen to have our classic starting point with the subject, here's a resistor, here's a capacitor, here's a switch, here's a voltage source, direct current, 10 volts, whatever. I always pick that number because it's so easy to compute with it. And the switch closes at t equals 0, or 0 plus, they say, immediately after the switch closure. The voltage on this thing will build, and the current through it will start out immensely high and then drop to nothing. It won't go below 0. But you're going to have a process where there's a time lag, and we also discussed the fact that this time tau, which is equal to this resistance R times this capacitance C, is going to represent where this will sink to 37% of the starting point. That's the starting point. This thing will grow to 63% of the final voltage up here. And that number comes from the 37 or 63. It comes from the fact that the property of the root of all natural logarithms, 2.71828. Most common logarithms have base 10, so it's 10 raised to some power. If that is your log. In the natural log world, it's to this number, which happens to be this irrational number. And it's natural because it actually, if you study trigonometry, is what you discover is the logarithm that fits into the pattern of angles and side adjacent, side opposite, hypotenuse, things of the right triangle. And when you have this value, this divided by this is about, it's about 1/3, which means it is 37% approximately, or 1 minus that is going to be that other half of the growth or decay curve. Okay, so we have this property where things build up or they decay over time when you put them through a capacitor, or the same would be true if you put them through an inductor. You would immediately get a voltage on this thing that would decay, and you get a current that starts at 0 and builds. So where in a capacitor, this is your voltage building up and your current decaying. If it's an inductance, flip them around. In an inductor, it would be the current building up and the voltage decaying. Perfectly equal and opposite characteristics. This is so amazing about inductors and capacitors. They don't look anything like each other. They store energy in totally different ways. This one does it in the electrical field between the two charged plates, where if you have a positive charge and a negative charge facing off against each other, you have an electric field. You have one in the middle of an atom. talking to the orbiting electrons. That's what holds the thing together. And this guy does it in the magnetic field that always exists whenever you have current flowing through a wire. All right, what if you had the same circuit, but instead of feeding with direct current, we're going to feed it with alternating current. So you don't have voltage that is constant, you got a voltage that changes like this. Think about what's going to happen. Well, you apply the voltage, and charges will build up here. I talked about this in the first class. And even when this thing is decaying, until you get to zero, charges will continue to build up until it gets fully charged. And then you get to the negative point where you're going to start drawing the charges out. And eventually, the minuses will be pluses, and the pluses will be minuses. And that capacitor will be charged in the opposite direction. But there's this time delay. It took until this period of time for the voltage to build up. It took this period of time for the current to, because of the charging up, for the current to decay down. So what's going to happen here is, if you have a capacitor here, immediately when you put your voltage source to work, this is the current flow. And starting 90, it actually turns out, if you look at the timing of this, exactly 90 degrees later, there's your current, this will be your voltage. The current will lead the voltage. It seemed almost impossible to think of a situation where, how is it that you get voltage and not current doing the same thing? After I put a voltage in something, current flows. And when you stop putting a voltage on, the current stops flowing. It's because that's storage capability. Because this thing is storing up energy. You've got current flowing through it, and the voltage that results from that takes a little longer to get there. You close the switch, you immediately get current flowing, which decays down. You have voltage build up, which happens later. So you are going to have current and voltage out of phase. And if you have this constant oscillation from 0 to a maximum plus, to 0 to a maximum minus, you know, the whole idea of what's alternating current is about, you're going to have two curves, not like three-phase power where there's 120 degrees between them, between each phase, but a 90-degree phase shift. And it's just between the voltage and the current. Here it's between three different voltages, 1, 2, and 3. Or what we call X, Y, and Z. If you ever look at a three-phase motor or generator or device of any kind, it's usually marked W, X, Y, Z. X is phase 1, Y is phase 2, Z is phase 3. W is only there if there's a neutral line, because in three-phase circuits, they can be wired in this fashion. We have 3 nodes. This is a so-called delta. Or you can have 3 nodes. Whoops. Yeah. It's supposed to be symmetrical. This thing should be going straight up. And it's called Y, except they spell it W-Y-E. And you can actually translate one into the other. And if you're going to, the reason things are usually sent using delta winding on these long transmission lines is because they don't have a neutral return. But at some point they need one. So they have a transformer that has a delta winding on the primary and a Y winding on the secondary, and they kind of converts it over from one to the other. The transformer actually has 3 separate windings in it for each phase. Okay, so you have this lag. And by the way, if there's an inductor, it's going to go exactly the same way in reverse, meaning starting 90 degrees late and continuing to be 90 degrees out of phase, you're going to have the voltage first and the current. Why the voltage first? The switch closes. If it's an inductor, it sees the magnetic field go through, produces the backward EMF, it produces a voltage here, and until that magnetic field collapses, the current is nothing. So the voltage will be the one that's immediate and decays, and the current will be the one that builds up over time. How do you keep these things straight in your mind? You have a cheat sheet with a little, memory trick in it. And the memory trick is this. Eli, the Iceman. Okay, what does that mean? Well, Eli's got an L in the middle, which tells you it's an inductive circuit. Ice has a C in the middle, which tells you it's a capacitive circuit. So this guy's an inductor. This guy's a capacitor. And what do you have here with the inductor? The voltage leads the current. What do you have with the capacitor? The current leads the voltage. That's how you keep them straight. But the conceptualization ought to be there for you. You look at the thing, it's charging up, current's immediately surging into a capacitor, the voltage builds up. With the inductor, as soon as you throw the switch, current doesn't want to go through it because that magnetic field expanding through it. And when that magnetic field's reached its final resting point, or whatever point you want to call it, expansion point, the current will start to flow, the voltage will drop. So there's how you think about it. There are definitely problems in the tests that go for general and extra that we'll ask questions about. Okay, I've got a capacitor and I've got an inductor, and both of them happen to be 100 ohms. I think I hopefully mentioned that omega is the symbol for ohms, and this guy's 100 ohms. We know that's intrinsically what the resistor is. We know that this is a function of frequency, so that X sub C has to be 1 over 2 pi times the frequency times the capacitance, or in short form 1 over J omega C. Omega is 2 pi F. The frequency, the number of times you turn the circle, 2 pi radians per rotation. And the J is just a bookkeeping device. Okay, let's talk about that. What kind of bookkeeping device am I talking about? It's called the rectangular coordinate system. I think you saw that before in your life. It was there when you took college algebra, if you took college algebra. It was there if you took basic algebra, I think. That was part of it. It had X in the horizontal and Y in the vertical. You remember those things, sure you do. Is there another coordinate system? Yeah, it's actually called the polar coordinate system. We're going to talk about that for good reasons, because we can actually use it to our advantage. Oh, excuse me, but this thing just doesn't want to erase. Let me get some.
The pen doesn't write and the eraser doesn't erase.
You know what it is? Yeah, I know, completely struck out tonight. Can't write, can't erase. Well, I'll go home. Useless. I'm doomed. Alright, newspaper tells you good for something. A little spritz and we'll be in good shape. Then the markers really won't work on a wet surface. A little house cleaning here. Yeah, that works. I remember the first time I ended up using something that wasn't a dry erase marker. And you couldn't erase it with anything. Had the housekeeper come out with something like, Windex. That was at one of these weekend retreats or some, convention center things where I had to give a talk on something. All right, let's kind of take a close look at this. This is really going to be useful because it's on the test. stuff you learned in high school somewhere along the line, whether you're right or not, goes there. A couple of other letters that are worth using alongside of R, as in real, and J as an imaginary. I've used I, but you know that was used for current, so J, of course, is the square root of -1. All I'm really saying is that's an imaginary axis, that's a real axis. If you took analytic geometry was the course, you would have equations of the form y equals ax squared plus bx plus c. Those are called conic sections. They are second order functions because the highest exponent is 2. And they would describe either a parabola or a hyperbola or an ellipse or some default or a circle. All those things could be defined by equations in this form. I think you have to also put in something like a couple of things. There were also terms of ax squared, bx, where you had rotation and translation, so the center wasn't necessarily at the origin, the point in the middle. And remember an equation like this one, minus b plus or minus the square root of b squared minus 4a c all over 2a. Anybody remember that?
Yes.
A quadratic equation? What was it doing? It was solving this equation. It said, what's x?